Hello everyone, welcome back to my channel. Today, we'll be going to learn a very important theory on coordination compounds, which is nothing but the valence bond theory. So as we have learned in our previous video, what a coordination compound is, what are the various terms in coordination compound. Then we learned about the Werner theory, where we have studied that how actually coordination compounds are formed and what are the basic characteristic of a coordination compound. As we have learned in Werner theory, that there are some points in which Werner theory cannot have a definite answer, like what is the structure of a coordination compound, what are the various geometries of a coordination compound, what are the colors, why they are color, and what is the magnetic property, the magnetic and the optical property of coordination compounds. So today, with the help of valence bond theory, we'll be trying to learn about the geometry as well as the magnetic property of coordination compound by using valence bond theory. So first, let us try to see what is valence bond theory and what are its postulates. So coming for the postulate of valence bond theory. In this approach, the basic assumption made is that the metal ligand bond arises from the donation of electron pair by the ligand to the metal atom. So remember that in this approach, the basic assumption, as we know that what is a coordination compound? So basically there is a donation of electron pair from the ligand towards the metal atom or ion. Okay, and then it arises, or it actually gives rise to nothing but the metal ligand bond, which we call as coordinate covalent bond. Okay, the second point in valence bond theory, if you see in your screen, in order to accommodate these electrons, these metal ions, okay, must possess requisite amount of vacant orbital of equal energy. So obviously, if one orbital gives you a pair of electron, let's say if a coordination complex is there where there are 6 ligands, then the metal must have 6 empty orbitals so that it can accept 6 pairs of electron, because one orbital can take 2 electrons. If a ligand donates a pair of electron, we need empty orbitals so that it can the metal can accommodate it. So remember that the basic criteria for a metal to form a coordination compound is it must have the required number of empty orbitals. And remember that these orbitals are obtained by the hybridization of the orbitals of the metal atom to give you a set of hybrid orbitals of equal energy. Okay, not only equal energy, but the bond will be of equal strength as well as will be directional in nature. So you will get a particular geometry from a particular hybridization. So valence bond theory takes into consideration the hybridization concept. Okay, now coming for the next postulate, as I have already told you that once this hybrid orbital will have, then in this hybrid orbital, the electron will be donated by the ligand. Okay, and it will, the bond will be of equal strength as well as will be directional in nature. Now the question is, what kind of hybridization gives us what kind of structure? Whenever we talk about octahedral, then always remember that there are 2 types of hybridization. We call it D2sp3 or sp3d2. We'll be coming into detail understanding of this particular hybridization in examples. We can have for square planar dsp2. For whenever it is dsp2 hybridization, it will be for square planar, and whenever we say tetrahedral, it is sp3 hybridization. So now the basic question is, how do we know that which particular metal atom is what hybridized, and how to understand this? So to understand all this concept, that which metal atom will be what hybridized, which particular metal, the coordination complex will be which geometry, okay, what will be its magnetic nature. So to understand all these things, let us try to go on with some examples. Okay, so coming for the examples. So let me start with a very common example. Okay, a very easy example for the first as a first example. So let me start with this particular complex. Let's say we have CR NH3 6 3 plus. Let us take this coordination compound. And now what we'll try to do is, we will try to find out its hybridization, we'll try to find out its geometry, we'll try to find out its magnetic nature. Okay, so how to do it? What are the different steps? So, and we'll be showing you all the steps. So the first one will be, what we need to do is first find out the oxidation number of the central metal atom. The first step is oxidation number of Cr, that is the central metal, in Cr NH3 6 3 plus. So how much it will be? If you try to find out the oxidation state, you will get it as +3. Okay. If you are not able to understand this, let me just do in this rough that Cr is X, okay, which we don't know. NH3 is a neutral molecule. There are 6 of it. So 6 into 0, charge is 0, will be equal to +3. Okay. So X will be equal to +3. Okay. So that is how we get it. Simple. Okay. If you are not able to calculate the oxidation state, or if you don't know how to calculate, please watch the previous videos where I have discussed how to calculate the oxidation state of various metal atom in a complex. Okay. Once we get the oxidation state, the second thing which we'll be going to do is write its electronic configuration. So electronic configuration of chromium, electronic configuration of Cr. Okay. So if I write the electronic configuration of chromium, it will be argon. Okay. So argon, I'm writing a noble gas configuration. Argon means 1s2, 2s2, 2p6, 3s2, 3p6. Okay. Then you will have argon 3d5, 4s1. Remember that chromium has exceptional configuration, right? Because of the higher stability of the half-filled orbital, we write 3d5, not 3d4, 4s2. So that part you need to be careful of. Then we need to write as we know that it is in +3 oxidation state, not as chromium atom. So next what we need to do is write the electronic configuration of Cr3 plus. Okay. So electronic configuration of Cr3 plus. So if I remove this 3 electron, so what I'll get is argon. Okay. Then 1 electron I'll remove from S and 2 electron from D. Total removal of 3 electron, not +3. So it will be 3d3. So once we are done with this, then the simple thing is just to now write the configuration. So hence, so if I'll just draw the configuration for Cr atom. Okay. So for Cr atom, how to draw the configuration? We know that it has 3d5. Okay. So 1, 2, 3, 4, and 5. So this is 3d. Okay. Then the next one is 4s, definitely. And after 4s comes 4p. Although it is empty, so we need empty orbital, as I've already told you. Okay. So now if I just draw the configuration 3d5, so it will be 1, 2, 3, 4, 5, and 4s1. So that is the configuration of chromium atom. Now we know that it is not present as chromium atom, it is present as Cr3 plus ion. So if it is present as Cr3 plus ion, then what will be the configuration of Cr3 plus ion? So again, the same thing. Okay, same 3d orbital. Okay, then you will have 4s, and then you will have 4p. Is it not? So again, 3d, 4s, and 4p. Okay, so now it's 3d3. So 1, 2, and 3. Okay. Now, once we are done with this, now the next question is, what is the hybridization? So over here, you need to understand a few things. As I have told you that a ligand will donate a pair of electron to the central metal atom. So it donates a pair. So one ligand will donate 1 pair of electron. Is it not? Now try to understand how many ligands do you have, or how many bonds that central metal atom is forming. Instead of ligand, just try to calculate the bond. So as we know that NH3 is a unit-entered ligand, one NH3 will form one bond with the ligand. So 6 NH3 will form 6 bonds. Okay. So 6 pairs of electron will be donated to the central metal atom by NH3. So we need a pair of 6 hybrid orbitals. Now, which hybrid orbital or which orbitals will hybrid or mix? So you can clearly see you need 6 orbitals. So you can clearly see in that D you have 2 D orbitals. Okay. Then you have S orbital and 3 P orbital. That means you have D2, S and P3. A total of 6. So the hybridization which we need to, or which this particular atom will undergo, is D2sp3 hybridization. Okay, so it will undergo D2sp3 hybridization. So basically it is mixing. So your 3D will remain 3D. This will not change, but the other will mix, okay, and give you a set of 6 orbitals. And this will remain 3D, no doubt, but this will combine to give you D2sp3. Okay, so once this, now we have this hybrid orbital. Now all this orbital, see, if you see in the previous case, what is happening is there is 2D orbital, 1s orbital, 4 and 3p orbitals. Okay, so as a result, they will have different shape, different bond energy, okay, different structure. So as a result, when they mix, now what will happen? Their bond energy will be equal, their geometry will be equal, their bond length will be equal. As a result, it undergoes hybridization. Obviously over here 3D will remain 3D. And lastly, what will happen is now it will undergo formation of the complex. So formation of the complex. So the complex which it forms is nothing but CrNH3 6 3+, where this 3D3 will remain 3D3. This will be unhybridized. So 1, 2, and 3. The next set of orbitals, now what will happen is it will hybridize. Okay, now once it has hybridized, so what will happen? Now the electron pair will be donated by ammonia. So ammonia will donate pair of electrons, 6 ammonia, 6 pair of electron, 1, 2, 3, 4, 5, and 6. Just to make it clear, you can mention over here that 6 electron pair donated by 6 NH3 ligand. Okay, so that is how we can understand that from where the 6 pairs of electrons are coming. Now, to conclude, so what is the hybridization? So the hybridization which we got for this particular central metal atom is nothing but D2sp3. And as we have discussed in the postulate that whenever it is D2sp3, the geometry will be octahedral. Okay, so CrNH3 6 3+ will always be octahedral. And next, whether it will be paramagnetic or diamagnetic. As we know from our basic concept of paramagnetism and diamagnetism, if there will be unpaired electron, then the system will always go for paramagnetic character. If the system will have paired electron, all the electrons will be paired, then it will go for diamagnetic character. You can clearly see in 3D, it has 3 unpaired electrons, which makes it paramagnetic. So why it is paramagnetic? Due to the presence of unpaired electron in 3D orbitals. So that is how we can conclude. So in exam, if they ask you that what will be the paramagnetic character of what will be the magnetic character of CrNH3 6, you can say paramagnetic. You can prove in this way. If they'll ask you what will be the geometry, you can prove in actually it is octahedral. If they ask you that whether it is which hybridized, then you can do in this simple way. So all the 3 actually questions can be solved by the same way. Okay, so that is how actually we do this kind of problems. Okay, now let us go for some other examples. Okay, so let us go for the next example. That will be COF6 3-. Okay, again in the very same way we'll be going to do it. The first thing which we'll be going to do is find the oxidation state, I'm writing OS. Okay, so oxidation state of CO in COF6 3 minus will be equal to, so again, let me just show you in rough. So it will be X, okay, plus 6, and fluoride is -1. Okay, the ligand is fluorido or fluoride, and total charge you can see in the complex is -3. So X minus 6 will be equal to -3. So X will be equal to +3. I hope you can get it, right? So this will be +3. Then electronic configuration, I'm writing EC of cobalt will be argon. Okay, atomic number of cobalt is 27, so it will be 3d7 4s2. Okay, then electronic configuration of CO3 plus, because we know that it is not present as cobalt, it is present as CO3 plus. So you remove 3 electrons, simple. So it will be 3d6, 2 electron you remove from 4s2, 1 electron will be going from d orbital. Okay, then hence now we just need to draw it again. So first we'll draw for cobalt atom. So cobalt atom will be, okay, 3d, then next will be 4s, and this will be 4p. Okay, now 3d7 4s2, so 1 2 3 4 5, always follow Hund's rule. Okay, first always singly put them in the orbital and then only pair it up. Okay, 6 and 7 and 4s2. Then going for the next now, so what we need to do is CO3 plus ion. So CO3 plus ion will be, so what we'll be going to do now is write the same orbital again. Okay, now we just need to remove 3 electron. So if I remove 3 electron, I'll get 1 2 3 4 5 and 6, 3d6. Is it not? Now the next thing which we need to do is now find out how many orbitals do we need. Very important. Now there are 6 fluoride ligand, fluorido ligand. The 6 fluorido ligand, it will actually donate 6 pairs of electron, F minus ligand. It is unidentate, so it will form 6 bonds. So the ligands are donating 6 pairs of electron to the metal. So the metal needs 6 empty orbitals. Okay, so if we need 6 empty orbitals, how many orbitals do we have? We have S and P3. So we have only 4. Okay, so if we have only 4, can we accommodate 6 pairs of electron? Definitely not. So what do we do is we will be using outer d orbital. After 4p comes what? It's 4d. So this time we'll be using outer d orbital because we do not have the inner d orbital available for bonding. They are actually occupied by 1 electron. Okay, so this is 4p, this is 4s, and this is 3d. So now you can clearly see you have 1 4s, 3 4p, so total 4, and you will be using 2 other from the d. The rest you will not be using. Okay, so what hybridization it will be? It will be sp3 d2. So that's what I have told you. Okay, it is d2 sp3 hybridization or sp3 d2 hybridization. Both are octahedral geometry. So I'm just showing you 2 different examples. Okay, just to make it clear. Okay, when it will be sp3 d2 and when it will be d2 sp3. Okay, so sp3 d2 hybridization. Okay, so hybridization. So once we'll have that, then what is our job is just to write the unhybridized orbital as it is. Okay, so we'll just write the unhybridized orbital as it is and then mix the other 6. Okay, so if I'll mix the other 6, so 1 2 3 4 5 and 6, which is sp3d2. Okay, then once we are done with that, then finally it is the formation of the complex. Okay, so we just need to form the complex. So formation of complex. So how the complex will be formed now? So obviously again you write the same, it will be remaining exactly same. So it will be same, 3d will be remaining same, there will be no change in 3d. But now in this 6 empty hybridized orbital, what will happen is this 6F minus ligand will donate a pair of electrons. So you can see I'm filling up the 6 pairs of electron. So again, where this 6 electron is coming from, 6 electron pair donated by 6 NH3 ligand. Sorry, not 6 NH3 ligand. That is a mistake. Is 6. Just let me clear it. It will be 6 F minus ligand. Is it not? F minus ligand. Now again, what will be the conclusion then? What is our hybridization? Hybridization is sp3d2, right? So now whenever hybridization is sp3d2, what is the structure or the geometry? Obviously octahedral. Okay. And whenever we talk about this, always remember that. Now, whether it will be paramagnetic or diamagnetic, you can clearly see there are 4 unpaired electrons, right? So that 4 unpaired electron makes it paramagnetic. This is very simple problems. Okay. You just need to understand how to do it. That's all. Okay. Now let me just show you one case, okay, where there usually students get really confused that whether it will be D2sp3 or sp3d2. Okay, so I'm just trying to show you one particular case. So these are the two straightforward case. In one case we have D2sp3 and another case we have sp3d2. So let me go for the next case. This is the case where students get really confused. Okay, so this is something which valence bond theory cannot explain also. Okay, this is the limitation of valence bond theory, which we'll be trying to do once we reach crystal field theory. Okay, but let me just show you. So it will be FeCN6 3 minus. Okay, so FeCN6 3 minus. So in this case, let us try to do it again. Okay, so first thing what we need to do is find out oxidation state OS of Fe in FeCN6 3 minus. How much it will be equal to? Again, let me show you. X, okay, that is the oxidation state of iron plus 6 cyanide 6 minus 1, okay, Cn minus, okay, will be equal to minus 3. So X will be equal to minus 3 plus 6, which will be equal to plus 3. So this will be plus 3. Okay, so once we get that plus 3, then what will happen is electronic configuration of Fe will be equal to argon, atomic number 26, so it will be 3d6 4s2. Then we know that it is not present as Fe, it is present as Fe3 plus. Okay, so what we'll be going to do now is we'll just remove 3 electron again in the very same way. Okay, all the things are same. 3d 5, 2 electron from S, 1 electron from D. Once we are done with that, then we'll just draw the electronic configuration. So it will be Fe atom. Okay, so what will be the configuration of Fe atom? We know that first it will be 3d, then 4s, then 4p. Okay, so let me just draw that 3d, 4s, 4p. Now it is 3d6. So 1, 2, 3, 4, 5, and 6, and 4s2. Right? Very clear. Same way again. So Fe3 plus ion. Okay, ferric ion. So what if I'll do that? Okay, so what I will get is now 3d5. Is it not? So if I'll fill it, so 1, 2, 3, 4, and 5. So I have 5. Now it's clear, right? Now again, it is the same kind of problem which we have done just earlier, that we have S and we have P. Okay, so we have 4. You can see there are 6 cyanide ligands. So obviously it is unidentate, from 6 bonds, 6 pairs of electron. We need 6 orbitals. We have 4. So what we can do is we can take outer d orbital. Same way what we have done just now for COF6 3 minus. But over here we don't, or it will not use the outer d orbital. It will use the inner. It will use that 3d. But you can clearly see in 3d, all the 5 orbitals are singly occupied. They are not empty. We need empty because they are giving us a pair. In an orbital, I can put only 2 electrons. It already has 1. So if I put 2, it will become 3. Now the question is, it should be sp3 d2 hybridization outer, but it will go for d2 sp3. Now, this is something which is actually a limitation of valence bond theory, which valence bond theory cannot explain. Now, let me just give you a slight information about this. Once we come for crystal field theory, then in our next video, I'll try to explain you everything about the crystal field theory and why it is happening. For now, just to understand this particular topic, always remember that ligands are classified into two classes. That is what we call a strong field ligand and weak field ligands. Whenever you have the presence of strong field ligands, okay, some very common strong field ligand which you usually encounter in your course is cyanide, carbon monoxide, ammonia, and En. En stands for ethylene diamine. This four, okay, usually which we encounter, very common in most of the complexes. These are categorized as strong field ligands, okay. So this we can classify based on crystal field theory, not on the basis of valence bond theory. The biggest limitation of valence bond theory is that it cannot explain that why some ligands are called strong field, while some ligands are called weak field. But it was found out that in presence of a strong field ligand, the configuration of the central metal ion tends to change, and the electrons, if it remains or if it is there in the central metal atom as an unpaired electron, then it tends to pair up. Okay, that is what we call as going for a low spin state. Okay, so the electron tends to pair up in presence of such ligands. Okay, and whenever you have other ligands, just like what we have done in our previous case, COF6, if we have fluoride, chloride, bromide, S2 minus, all this, okay, usually the anionic ligands, okay, not all, but some, like the halide ion, are considered as weak ligands. And in presence of such ligand, the configuration of the central atom remains unchanged. If there are number of unpaired electron, it will not pair up. But in case of this four, especially this four, which is very common in your examinations, whenever you encounter such ligands in complex, always remember that the configuration of the central atom changes and the electrons tends to pair up. The full explanation of this you will be trying to do once we actually go for the crystal field theory, okay, which will be in our next video. But remember that whenever you talk about this particular topic, okay, remember that whenever you have all this kind of ligands, okay, CN, CO, EN, NH3, I'll give you the detailed explanation that which other ligands are called strong field, which ligands are called weak field, okay, once we reach crystal field theory. But for now, always remember that whenever you encounter this kind of ligands in valence bond theory, you need to pair up the electron. The configuration of the central metal atom or ion changes. Be very, very careful, because this creates confusion, okay. So that's why I've given you this four specific ligands, which are very common in your examinations. Okay. So whenever you get this four ligands, what you need to do is pair up this electron. So what will happen is, if I just draw it. Okay. So the electron tends to pair up as much as possible. Obviously, there are 5 electrons, all cannot pair. Okay. So the electrons will pair up as much as it can. Okay. So remaining 2, right? So this 2 will now hybridize with the other 4. So total 6. So see, it is not going for sp3d2, it will go for d2 sp3. Most of the students, they make mistake in this. Okay, they go for sp3 d2 hybridization for k FeCN6 3-. Okay, which is not the case. So please be very careful. So this will be 3d. Okay, and then the rest, which are empty, will undergo hybridization. So if anyone will ask you what is the hybridization of FeCN6, it will be D2sp3, not sp3d2. Okay, so it will be D2sp3 hybridization. Be very, very careful in this. Okay, very common questions in your examination. So what we need to do is, now we have this, and finally it will go for formation of the complex. Okay, so formation of complex in which the unpaired electrons and the d orbital which are paired will remain as it is. Okay, and in the hybridized orbital, now what will happen is electron will be donated. Sorry, there will be six. So six. So it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 6 pairs of electron. That will be D2sp3. Now, who is donating this electron? It is the 6Cn minus ligand. Okay. Donating 6 pairs of electron. Okay, to the central metal atom. So that is how. So this will be very, very important. Okay, please remember this 4 ligands. Okay. This particular point cannot be explained by valence bond theory. Always remember that what is the difference between strong field and weak field. That's why we need crystal field theory to explain this. Okay. And later on in crystal field theory, we'll be learning about spectrochemical series where we distinguish that which is strong and which is weak. Okay. So now what is the conclusion for this? So it is D2sp3 hybridization, not sp3d2. Again, I'm repeating that. No doubt it will be octahedral and paramagnetic or diamagnetic. Can you see there is one unpaired electron over there? That makes it slightly paramagnetic, not that very high paramagnetic, but yes, it is paramagnetic. No doubt in that. Okay. So that is how we can understand. Okay. So that is how actually we can explain that in which case it will be D2sp3 and sp3d2. Now, very important part. Always remember that whenever we talk about this D2sp3 and sp3 D2sp3 and sp3d2 hybridization, whenever you have these two types of hybridization in octahedral complex, with reference to this hybridization, we have classified the octahedral complex into 2 categories, which we called as inner orbital complex and outer orbital complex. So all those complexes where the inner d orbital, that means D2sp3, which we write as n-1 d orbital, that is the inner orbitals are used. Like in our case, it is 3d orbitals which are used, right? So it is D2sp3 hybridization. So whenever it happens, we call it inner orbital complex. And in this type of complex, if you see, most of the electron tends to remain pair. So usually this type of complex, the inner orbital complex are diamagnetic. And if they are not, they will have very less number of unpaired electron. Okay. They will be not that very highly paramagnetic complex. Okay. And whenever we talk about sp3d2, okay, it will be the outer orbital complex, which we actually, it will be the outer d orbital, which will be used, which we have seen in case of COF6 3-, the outer orbital, 4d orbital, which we represent as nd orbitals. Okay, so the hybridization, whenever it is sp3d2, we always call it outer orbital complex. And remember that in this type of complex, the number of unpaired electron tends to remain more because the configuration of the metal remains unchanged. Okay, that's why they are also called high spin complex. So always remember that inner orbital complex, low spin complex, outer orbital complex, high spin complex. Okay, so that is what you need to understand. Okay, now let me go for more examples. Just let us take one example for the octahedral. We have taken example for octahedral complex. So let me just take some example of square planar and tetrahedral complex. So let me take first this. Okay, so it will be NiCO4. Okay, nickel tetracarbonyl. Okay, so when we have nickel tetracarbonyl, how to actually go for this particular hybridization? Okay, so for how to find out its hybridization or its structure? No, so first again, oxidation state of Ni in NiCO4. Okay, so if I'll go for that, then Ni obviously is X. So X plus 4, carbon monoxide, it's neutral. So 0 will be equal to 0. It's a neutral complex. See, nothing is there outside the coordination sphere, no charge, right? So, or coordination entity. So what we can write is X will be equal to 0. So it is 0. It is present as nickel atom, not as ion. So electronic configuration of nickel. So electronic configuration of nickel will be obviously atomic number 28. So argon 3d8 4s2. Okay, so once we actually get that, then hence Ni atom. I hope you can understand. I'm not writing electronic configuration of any ion because it is oxidation state 0, so it will not come, right? Ni atom. So Ni atom, so 3d. Okay, then 4s and then 4p. Okay, so 4p, 4s, and 3d. So 3d is 8, 1, 2, 3, 4, 5, 6, 7, 8, and 4s2. Now, obviously, it is present as nickel atom only, so we have to directly go for hybridization. Now, before going into hybridization, always in valence bond theory, whenever you do it, now, as I have told you, you have to go for this particular ligands. See, it is CO. I have told you that CO is a strong field ligand. So if it is a strong field ligands, the electron tends to pair up. Okay, so what hybridization it will undergo? So first, the electrons will pair up. You can clearly see that there are 2 electrons over here, okay, which are unpaired in d orbital, and 2 electrons are present in 4s. So this 4s electron will be shifted to d orbital. So it will be 1, 2, 3, 4, 5, 6, and this 2 electron will come and it will pair up. So all the electrons will be paired up in d, and as a result, this 4s orbital will become empty. How many orbitals you need? 4, because there are 4 ligands, 4 unidentate ligands, 4 unpaired electron, 4 pair of electron will be donated, 4 bondings, right? So you need 4 orbital only. So which are those orbital? They are s and p3. So hybridization is sp3. So it is sp3 hybridization. Okay, so once we get sp3 hybridization, now our next job is just to make the complex or formation of complex. How the complex will form? The complex will form by donation of electron pair from the carbon monoxide ligand to the central metal atom. So 3d orbital will remain as it is, and the sp3, okay, now we'll get 4 unpaired electron from, 4 pair of electron from 4 CO ligand. Okay, so these are the 4 electron pair, 4 electron pair donated by 4 CO ligand. Okay, so once we are done with that, then just the conclusion: hybridization sp3. Whenever it is sp3, it is tetrahedral. Okay, and finally, what is the magnetic character, paramagnetic or diamagnetic? You can clearly see you don't have any unpaired electrons, so it is diamagnetic. Okay, so that is how actually we can understand that, how to get the tetrahedral geometry. Okay, now let me take one last case, okay, which will be for the square planar complexes, which will be NiCN4 2 minus. Okay, so let us try to take this. This is square planar complex. So how to get it? Again, same way, electronic oxidation state of Ni in NiCN4 2 minus will be equal to, if you calculate it, you'll get +2. Okay, then electronic configuration of Ni will be equal to, so electronic configuration of Ni, again same thing, it will be argon 3d8 4s2. Then now it is ionic form, so electronic configuration of Ni2 plus. So what it will be? It will be argon 3d8 2 plus 4s2 will go, right? Then hence it will be Ni atom. So Ni atom will be equal to 1, 2, 3, 4. So 3d 4s 4p 3d8 1, 2, 3, 4, 5, 6, 7, 8 and 4s2. Okay, then Ni2 plus ion. Okay, so now what will happen? Obviously, it will lose 2 electrons. So it will be 4s2, which will be lost. Okay, so it will just get 3d8. Okay, now here also you have to be very careful. Remember that it has a strong field ligand, Cn minus. So again, the electrons will pair up. Okay, so that part, please be careful. So once you do that, what you'll get is the electrons will be pair up. Okay, so this electron in D will be shifted to the another one. Okay, most of the students take it as sp3 because they can see clearly that this 4 ligands are empty. No? So sorry, these 4 orbitals are empty, so they tend to mix that, forgetting about the strong field ligand, the presence of strong field ligand. Okay, so it will not be actually sp3. Okay, so it will be D2sp3. Okay, so whenever we have this kind of cases, always be very, very careful. Okay, very, very careful in doing, because you may make, most of the students, they do make mistake. Okay, because they just take the orbitals, they don't keep in mind that strong field ligand changes the configuration. So it will not be sp3, it will be this D orbital will always be actually taken, the lower one. So it will be D and S and P2. You need just 4 because there are 4 cyanides. So it will be DSP2, not sp3. Okay, so that part you be very, very careful. So it will be DSP2. Okay, so just a minute, it will be DSP2. Okay, so it will be D, just a second. Okay, so it will be DSP2 hybridization. Okay, so it will be DSP2 hybridization, and that will be your empty orbitals. Then finally it will go for formation. So formation of complex. So how the complex will form? Same thing. Okay, so obviously now you'll not have 5 empty orbitals. Okay, let me just draw it again. So you will have 4 3D. Okay, 3D and 4 orbitals. One will be hybridizing, and in this empty hybridized orbital, 4 unpaired electron will be donated by 4 cyanide ligands. So it will be D2sp3. So it will be, sorry, DSP2. My mistake. DSP2. It will be square planar, and it will be diamagnetic. You can clearly see there is no unpaired electrons. So that is how we can understand this valence bond theory. Very, very important. Okay, so that is how we need to tackle the problems based on structure, based on paramagnetic character or diamagnetic character or hybridizations. Okay, the only thing which you need to keep in mind is the strong field ligands. So that part, if you can actually understand, then the other things you can easily do it. Okay, and why the strong and the why it is the why there is actually the difference. What is the difference, basic difference between strong and weak field ligand? We'll be definitely trying to do in our next video, that is on crystal field theory. Okay, so now let us finally go for the limitation. Okay, so the limitation of valence bond theory. So remember that valence bond theory cannot explain that why some metal complexes are inner orbital complex, some are outer orbital complex. There is no explanation. Okay, it tells us that one is D2sp3 and sp3d2. It tells us that it pairs up the electron in one case. Why it happens? There is no clear-cut explanation from the valence bond theory. The second point, it cannot give satisfactory explanation for the color, the optical property. Now, why they are colored? There is no such clear-cut explanation. Okay, it cannot give us the explanation for the stability of coordination complex, why they are stable, why they are unstable. Okay, so this particular part, the valence bond theory cannot explain us. And finally, it does not distinguish, as I have told you, between the weak and the strong field ligand. What is weak ligand and what are strong ligand? How do you distinguish this? This limitations actually, these are the points which valence bond theory cannot satisfactorily explain us. Okay, and that is why actually we need to go for the other theory to explain all these things. The explanation for color, the explanation for what are strong and weak field ligand, why it forms inner orbital complex, why it forms outer orbital complex. So all these things can be explained by the next theory, that is nothing but crystal field theory. So that is what we'll be going to do in our next video. So thank you, everyone. That is all for today's video. Do subscribe for this channel for explanation on various topics in chemistry. Thank you.